Luke Evans will speak about computing committer functions by means of diffusion maps. Committer functions are the crucial functions for quantifying rare events in systems evolving according to stochastic differential equations, especially in those that arise in the context of chemical physics application. This project was started at the beginning of funding by the Afosram Yuri grant. So I am going to share screen. Oh, please, Luke.
Hi, so after the nice introduction here, I'll go ahead and start talking about this joint work with Maria Cameron Parishtuari. I'm a PhD candidate at the University of Maryland, College Park, funded by the Muri Career Grant from Pratyush, as well as a dissertation fellowship. So as Masha mentioned, the area that we're looking at in this project is for molecular dynamics. So a molecular simulation in all atom coordinates for biomolecular systems that exhibit metastability, so that there are stable states, often defined, you can think of by collective variables, usually these dihedrals for this small molecule here, that determine stable states, and that the system will hang out for a very long time in these states on large timescales, and that with the computer simulation, it's long enough that there is an issue in running the simulation for this long to observe some sort of rare transition that happens when it happens very quickly, is with regard to the time step of the staying between the stable states. The system we'll keep coming back to here is this small 22 atom alanine peptide simulated in vacuum. The kind of full dimensionality you can think of in this case from data analysis is that if we're in phase space, so that we have 6 dimensions for each atom, we have a 132-dimensional system here. That in the simulation itself for Langevin dynamics is something that looks like Newton's equations, but that has a friction with a dissipation term here, and then there is a Brownian motion governed by beta inverse, which you can think of as a heat parameter. M for the little m is a mass matrix for the atoms. Gamma is the friction. The dynamics that we'll come back to is what one would typically see or try to approximate if a computational chemist or other domain expert would give you some collective variables, sort of variables that ignore the very small timescale atomic vibrations and say something more about the slow dynamics. For this molecule here, you usually think of it in terms of these 4 dihedral angles, and that if you're watching the simulation, it looks like these kind of wings flapping here. These dynamics are lower dimensional. In this case, you can think of a 4-dimensional SDE as opposed to 132-dimensional. That its most important thing that we'll come back to is that there's a position-dependent noise, which there was not previously. That depending on the collective variables X, there is a 4x4 M matrix here that determines the noise at a given spot, and that there is a forcing term, but that is not a gradient of a potential anymore. Now, briefly, I do want to say that in the model that we're looking at, these are not analytical in the collective variable sort of reduced model. The way the free energy and M are computed is through restrained simulations. The typical way of doing this is that if you have a particular set of collective variables, X, that you're wanting to look at, you add something to the potential function that keeps the trajectory sort of in a small region, and then create appropriate averages to get this, in this case, the mean force here, and then the diffusion matrix. The most important part that we'll come back to is that in this case, this 4x4 diffusion matrix comes from the derivatives of this mapping to collective variables with respect to atomic coordinates. And it is an average of Jacobians based off of a restrained trajectory. And these ellipses here and other pictures you'll see are for this 2-variable case. There's a 2x2 M matrix whose PCA gives you these coordinates that you can use to plot one of these ellipses. Our framework theoretically is going to be transition path theory. This is generalized from transition state theory in chemistry by Wen-An Oh and Eric van den Eijden, and also Wei-Ching Ren worked on this in 2006. the idea with this is sort of formalizing this notion of these rare transitions, where if you have two stable states, you can think of these as minima of some sort of potential function, where deterministic dynamics would descend into this minima and stay there, but that with noise, you occasionally get these rare transitions. The thing we're studying in transition path theory are reactive trajectories, which is that if you observed one long ergodic trajectory, you would see trajectories that leave A and enter B before ever returning back to A. And the statistics of these trajectories, the ones in black, are the ones we wish to analyze in transition path theory. And the quantity that you would look at for this is something called the committer function, which is the function that in this sort of abstract example, if you were to start your trajectory at a point X, you would want to know the probability of hitting the set B before you hit the set A. In transition path theory, this function is used to get a lot of other properties for the rare events. So that one of these is the reactive current, which is a vector field that can tell you where the pathways are likely to be for the reactive trajectories, and then the transition rate, which lines up with the traditional rate from transition state theory in chemistry. The way you'd get the committer is one way. You could do some brute force simulating. This is very high variance and very hard that you'd have to do this for each individual point. The more elegant way, but that is difficult to do, is to solve a PDE for the committer. What this PDE looks like, you can think of, is something that looks like Laplace's equation. If this L operator had, this was a sort of a uniform density here and M was identity, you would get the Laplace operator, so that you'd get LQ equals 0 off of A and B. The committer is 0 on the boundary of A because there is no probability of transitioning to B first at that point, and likewise for Q on the boundary of B. Some issues here is that depending on what domain you state this in, this is a very high dimensional BVP. If you stated this in the atomic coordinates case for alanine dipeptide that we talked about earlier, you would have a 132 dimensional PDE here. But even if we pick these 4 dihedral angles from earlier, we would have a BVP that we cannot solve with usual methods as far as finite element method and finite difference method goes. So the way that we're looking at this is sort of a dimension reduction problem, that we've gotten collective variables from some domain user, but that the BVP we're looking at is still probably too high dimensional to use conventional means. And so we'll use a point cloud based method that we'll mention in a second here. I do want to say that our goal is to get the committer, but that after this, there's these other quantities that we're also trying to get. On a brief 2D example here, if you have some sort of potential function with these two minima at A and B here, and you're trying to find the committer between them, the committer itself, if you're sort of to plot this on some sort of one-dimensional line here, would look very sigmoidal, that it stays near 0 around A, sharply goes up to 1 near B, and that there's sort of an interesting transition region here in the middle, which is kind of the interesting transition state from transition state theory that we'd be interested in studying. And then you have this region here where the potential is more flat. And it turns out this reactive current, which in this simpler case for the dynamics is essentially the gradient of the committer, weighted by the stationary density. The magnitude of that vector field shows us where the likely trajectories are when they escape from A to B. And the transition rate is a Dirichlet form here on the part of the domain between A and B. So in general, we're looking for this high dimensional problem and solving it with this Mahalanobis diffusion maps method. And that for 2 other kinds of ways people will look at this, there's tensor trains as well as neural networks, some of which we'll see in these other talks, that it sort of fits into this realm of people trying to solve high dimensional elliptic boundary value problems using some sort of machine learning technique often. So the way this fits in is with sort of other diffusion maps based approaches for this, but that there's also approaches with tensor trains as well as with neural networks, trying to minimize basically a variational term for a loss function. And so that in our case, we are looking at, let's see here. We are looking at, in our case, viewing our data and collective variables as some sort of point cloud. So that if we were using these 4 or dihedral angles as sort of our data points, we have some point cloud in 4D, which we're showing here in 2 of the variables, phi and psi, and also picking 2 others for this here, that if we made a graph on this point cloud and we're able to solve the BVP on this point cloud, we could get around some dimensionality issues here. The idea that if we have a trajectory, we would like to find some sort of discrete generator matrix L, so that when we apply L to some function on the point cloud, we will get accurate up to pointwise on this point xi here, what the continuous operator would have gotten. If we can find such a matrix, then we can solve this boundary value problem here, and then have a discrete representation of the committer on this point cloud. So that in this case, for 4 variables projected down to 2, you can see the committer for these 2 regions defined in the space of dihedral angles here between A and B, probability going from 0 to 1. And likewise, if we pick 2 other variables here, which we'll come to later, how we're actually doing this and finding this L matrix here. The way in which we're doing this is with something called diffusion maps, which fits into this realm of Laplacian eigenmaps, also spectral clustering, if you're familiar, that where this idea of building some sort of similarity, pairwise similarity on a data set, taking the matrix from that and analyzing it to learn something about the data. For diffusion maps, it's done from a perspective of constructing some sort of Markov chain on the data set. That sort of the basic way of doing this is you construct a Gaussian kernel so that there's 2 pairs of data points, xi and xj. There's a similarity that drops off sharply once a point is too far away from this green point xi here. And that the main hyperparameter in this case is epsilon, which is determining this kind of Gaussian you can think of around each point here in the kernel. And that takes some practice to learn to tune, and there's other heuristics you can use for this as well. The Markov chain is proportional to this kernel matrix, and that the theory, which is part of why we wanted to use this, is that we have guarantees of the kinds of operator this approximates on the data set, given enough data, and that you're able to take this parameter small enough here. That when you have this Markov chain, you subtract the identity, rescale it, and you can actually have an approximation for some sort of differential operator L on the data. The catch being that it may not be the one that you're looking for. It's sort of like you're imposing some sort of dynamics in the data set, and that depending on how you construct this kernel and do other steps, you can get the operator you'd want for the data set. The sort of back and forth for this on the right-hand side is what it would look like if you coded this, that if you had your samples, you made your kernel matrix, there's 2 steps you do. You sort of create a vector of row sums, and you multiply this diagonal matrix on the right for your kernel. This is a right normalization that affects the density that you're going to get in your final matrix applied to data. And then you have left normalization here, which is taking this new kernel you have and turning it into a Markov chain. These, in theory, get these integral operators here when you have enough data points, and that because of this Monte Carlo sort of integration here, you can say what's being approximated here. This alpha parameter determines what kind of operator you can get in diffusion maps, so that the differential operator you get here, this first order term, it depends on the alpha you pick. That in our case, we're thinking of alpha equals 1/2. Usually for molecular dynamics, this has more dynamical significance here. You can also cancel this out entirely by picking alpha equal to 1. The term diffusion map in this case usually refers to when people will use this algorithm to find their discrete L matrix and then solve an eigenvalue problem with it and use it for some sort of embedding on the coordinates. In our case, we're instead using it for a boundary value problem, but this is where this diffusion map term comes from. The first extension we're using in our case of this algorithm is for collective variables. There is this more complicated SDE from earlier, and that instead of using a regular Gaussian kernel as earlier, we're using a kernel that is also based off of these diffusion matrices, these M's from earlier. This is originally introduced by Singer and Koifman for Mahalanobis diffusion maps, in the idea where your data set has been transformed by some sort of diffeomorphism, which you are undoing with this kernel. In our case, these M matrices do not take the form of J transpose for some Jacobian. There's no sort of transforming to another latent Z here. And so when we looked at this originally, we wanted to know how useful it still was to use this kernel. And it turns out that this kernel is what we need to approximate a differential operator with this position-dependent diffusion. So that we worked off of previous work with this to adjust according to our case, and then theoretically and numerically, we're able to show this. The next thing we looked at with this was target measures, meaning if we had some sort of advanced sampling procedure to get our data that destroyed the original sampling density we would like to see, we want to re-weight that to a density, in this case, that dealt with room temperature for the free energy for this molecule. For our case, we used metadynamics, which is something that for these 10 nanosecond trajectories gets the most coverage very quickly. It's an adaptive biasing potential that you change in the simulation to discourage points from returning to places the trajectory has previously been. Combining these together, in the blue, we have sort of our changes to this algorithm to look at the diffusion matrix M for the Mahalanobis diffusion maps. And in red, we have our target measure here, sort of relating to this free energy at room temperature for our reweighting. And we were able to theoretically show that these approximate the operators that we would like, and with some simple scaling that you can cancel out. And we are able to also numerically show this, which we'll show for two cases here. Both of these are coming out of our publication in Journal of Chemical Physics. These examples involve taking this L matrix we had from earlier and solving a linear algebra problem for the committer. And two other things which we don't have time to do, but we did discuss in this paper you can look at, are when the target measure is actually unknown to reweight to, and to also figure out this vector field that is the reactive current here. If we're just looking at two dihedral angles for alanine peptide and trying to solve the committer, in this case, we can actually do a model reduction error analysis with respect to the finite element method applied to these two variables. We can solve that PDE in 2D, and that's in these black lines here, and it lines up quite well with the committer. In this case, we're looking around this minima here because this is where the committer is non-trivial, this sort of transition region here. Likewise, for the current on the left is from our method that we can get quite close in the scale and also in the place sort of where the magnitude is non-zero. And for the error, we can compute something quite stable with respect to this bandwidth parameter, epsilon, that in the errors we compute here, as well as for the rates, so that here in this dotted black line is the finite element method rate for this two variable case. We can not only get very close to this, but over a very stable range of this hyperparameter, which can in general be difficult to tune, but that in this case is a wide range that works for.
What is delta net?
And so for the delta net in this case, that a big part of it is that we can figure out how to subsample this data set to improve the results. That for a trajectory that we've gotten from one of these enhanced sampling methods, for a delta net, we actually pick a radius delta by which to rarefy and quasi-uniformly sample this data set, which can hugely affect the error estimates for this method, and is a really simple subroutine to put in this, and that we will go over in later talks for how much this can really affect the error analysis and effectiveness of these methods. And that you can show from here that it makes, yes, and in Shashank's talk, we sort of talk about the same thing here, that for the delta net data set versus the kind of regular enhanced sample data set, that we have much better errors as well as the rate approximation here. Likewise, when we look at the 4-variable case, which is again moving out of this regime where we can test against the finite element method, we are looking at what I'd shown earlier, that if we have 4 variables for the CVs and that we solve for the committer using our method, we can project this onto different pairs of dihedrals to visualize this. And that for our case, when looking at this, these line up very well with previous literature on this subject. And that for the rates in particular, we found that for our 4 dihedral data set with target measure Mahalanobis diffusion maps, that we'd gotten quite a close rate estimate compared to a direct rate estimate that was computed in this work, which was really encouraging for that. So that for future directions with regard to the Mahalanobis diffusion maps and things that we're actively looking at for target measure diffusion maps are error analysis with respect to sampling density and target measure, which we'll talk about with Shashank. And also some other work to look at would be more assessment of model reduction error. We've used physically learned collective variables in this study, but that machine learned collective variables coming from some sort of neural network or autoencoder for representation learning that we could use to apply mmap to this and then look at the rate that we get to look at its sort of how well it's reproducing rates of the original system, and also scalability for these computing these M matrices and higher dimensions and for software packages. And so I'll stop there with that, and thank you.